the coil and magnet speaker has been our only means of experiencing sound our entire lives. And it was invented way back in the 1800s, kind of perfected in the 1920s, and just, slowly improved ever since then.
Can a new innovation upend a $50 billion industry that uses 100-year-old tech, still uses 100-year-old tech, and it is probably in your ears multiple times a day? Hello and welcome to TechFirst. My name is John Koetsier. Pretty much all of us use earbuds, maybe wireless, maybe wired. They all rely on pretty old tech. It's 100-year-old tech. Now there's a new option that's based on, of course, silicon. It's a microchip. It's a means of creating sound that is very different. It could be better while also being cheaper. Here to chat and give a big product announcement at some point is Mike Householder, a VP at XMEMS. Welcome, Mike.
Thanks for having me, John.
Hey, super pumped to have you. Let's start at the beginning. One of the things that I saw in the pitch when you said, hey, let's chat about this, was that headphones rely on 100-year-old tech. What is this 100-year-old tech?
Yeah, it's the speaker that we've all been using pretty much our entire lives. So the coil and magnet speaker, has been our only means of experiencing sound our entire lives. And it was invented way back in the 1800s, kind of perfected in the 1920s, and just, slowly improved ever since then. But it's a mechanical structure. It's got, first of all, a coil and magnet for actuation. You drive a current through that coil. It moves the magnet that then pushes through various layers of suspension, a paper or plastic diaphragm that moves air and generates sound. Fundamentally unchanged for 100 years.
Wow.
So what we're replacing it with is a solid state semiconductor alternative. So now instead of a complex mechanical system, we can produce very sophisticated, higher quality sound with a chip.
Wow.
So this is a speaker on a chip that can produce very sophisticated audio. So you're getting really all of the benefits of semiconductor technology paired with sound generation.
So let's unpack that a little bit and talk about what those benefits are. And it's really interesting because totally different industry, but about a year ago, I interviewed somebody and they're making a solid state silicon based fuse box for your home. And nobody thought it was possible. Nobody thought it could be done. And they did that. And you're talking about something that is a totally different space, but is somewhat related. It's solid state and you're using silicon chips to recreate this. Why is that a good idea? Why is that important to do?
If you look at the consumer electronics industry, there's just a natural gravitational pull to solid state components. They're scalable, more reliable, generally faster, better performing. And really, if we look at an average consumer electronics product today, be it a phone, a TV or whatnot, there are very few non-solid state components remaining in those devices. The one remaining one, for the most part, is the speaker.
You're coming after the last survivor.
Exactly. So, there are so many examples in the industry of a traditional mechanical device being replaced by a solid state semiconductor variant. I can walk through a couple of examples. If we go to the opposite end of the audio spectrum, the microphone, most people don't know the microphone is mostly semiconductor MEMS technology today for a majority of the microphones. The mechanical microphones still exist, but the majority of the unit volumes are MEMS semiconductors. For those who we all have phones and PCs today, the spinning mechanical hard drive, for the most part, has been replaced by a solid state drive. Why? It was more reliable. It's faster. You get your data faster than a traditional spinning mechanical variant. You brought up the fuse box. You look in automotive now, everyone's pushing towards solid state batteries.
Mm-hmm.
Once a solid state variant exists, it will over time take the majority of unit volumes for that function.
Okay, so that's a little bit about how it's constructed, how it's built, and sort of this overarching flow of the world of technology towards solid state. Why is this a good thing for speakers? Why is this a good thing for headphones? Here's some headphones that you sent me that I've been testing and trying out. Why is it a good thing to apply here?
Yeah, good question. So I'll answer that question from two angles. One is benefits to the manufacturer of the product, and then benefits to the consumer. All right. So to the manufacturer, they want a solid state component because, again, of all the quality and reliability advantages versus their mechanical variant. Easier to test, easier to scale. They're more uniform than a traditional coil-based speaker. And what I mean by uniformity is each speaker's loudness level is equivalent. Their phase alignment is more consistent. So that's what you want out of audio when you're trying to match a left and a right. You don't want them louder or quieter than the other side. You want them perfectly phase aligned so you don't muddy any of the audio response. So a solid state semiconductor is just going to be more uniform and consistent. It's going to be more reliable. It's going to survive a lot longer. It's going to survive drops and water and moisture and dust better than a mechanical variant. And it's
One of my original AirPods I dropped, and the audio was never the same after that.
Yep. Yep. So more robust to drop. One of the things we get asked by a lot of our customers is, well, could it survive a washer dryer cycle? Hey, who's left their AirPods in their jeans and run them through a washing cycle? So yeah, the answer is yes. You can run our speakers through washing machine and dryer and the speaker will work. We can't guarantee the rest of the electronics is going to work, but we can say confidently the speaker is going to survive. And we also remove the magnet. So we're taking out weight. We're taking out a source of electromagnetic interference with the wireless antennas and a wireless earbud. So those are really all the benefits to a manufacturer. They like solid state. So now, but the consumer may care a little bit less about whether it's easier to test or this or that. So really what the consumer cares about is audio quality. Are they going to, get better music quality by putting a solid state speaker in their ears versus a conventional speaker? So there are three unique aspects to our sound signature that a conventional coil-based speaker doesn't do and can't do. So the first characteristic, is really in the mechanical response of the speaker. The speaker actually moves up and down. Its mechanical response is about 150 times faster than a legacy coil variant. So what does that mean to the consumer? A fast actuation means that you're going to pump air and then you're going to recover and be ready for that next audio stimulus a lot sooner. So as the music gets really dynamic, really complex, lots of instrumentals, multiple voices coming in, you really care about detail and separation. You want to hear one instrument clearly delineated from the next instrument. You want to hear that background vocal as well as the front vocal, and you want to believe that they are all separate and unique. And the slower the speaker gets, speaking of legacy speakers, some of that detail starts to kind of muddy together and you lose that precision, that sense of separation. A faster speaker will present that detail in all its glory. So the speed gives you that detail and separation. So that's one unique aspect.
It's almost like having a higher resolution display, in other words.
Exactly. So it's the equivalent of, HD video. Now you're kind of really stepping into, there is HD audio, there's high res audio out there, but can the speaker truly resolve that content? Are you taking HD video and running it over a CRT monitor? Or are you pushing that HD video over a high pixel density HD screen? Same equivalent, same analogy on the audio side. The content may be HD, but can the speaker truly resolve that content and present all of that additional detail? That's what you can do with this speaker. So the speed is number one for the detail and separation. The second aspect of the sound signature is really flat phase response. So it's really not known and really not well known, but conventional speakers have a phase disturbance, a phase shift, kind of in a 500 to 2 kilohertz region, which is a really sensitive region of the human ear. But I think the human brain has adapted to it because it's the only way we've ever experienced sound that we just don't kind of hear that phase disturbance.
What exactly is a phase disturbance in
So,
sound?
so it's, the shift in phase will basically alter the original recording of the music. But again, I think the human brain has been tuned to just ignore it. But as you saw from that Brian Lucy video, he's a mixing and mastering artist in the music industry. His argument is, so these conventional speakers have a 180-degree phase shift at their resonant frequency, which is 500 hertz to 2 kilohertz typically.
Mhm. Mhm.
Our phase is flat out to 10K. There is no phase disturbance. There is no shift in phase. And, for a professional ear like Brian's, it was immediately apparent to him that, what he is mixing and mastering, how he wants the consumer to hear the audio, he typically doesn't find a consumer audio product that renders it as cleanly as he wanted you to hear it.
Mhm.
And
Mhm.
what he heard from our speaker with the kind of the pure phase response, he finally heard a speaker that presented the audio in the way he wanted it presented to the consumer.
Interesting. So that would be more aligned with how you would hear live music, for instance.
Correct. Correct. Um, and while we're on the phase discussion, this gets back to the uniformity and consistency out of the semiconductor process. Chip to chip, our phase consistency is there. So this really steps into spatial audio. So as you're moving audio from the left to the right, up and down, you want perfectly phase matched speakers to render that spatial content accurately and not muddy the spatial response. So
Mhm.
having perfectly matched left-right speakers that are perfectly uniform, you're getting more crisp and clear spatial audio.
Nice.
So so the phase kind of is in two aspects, the phase shift and the phase consistency. The third characteristic to our sound signature is really in the materials. So most speakers today use a diaphragm material that's, paper or plastic. There's certainly a lot more exotic variants as you get into really expensive speakers, but the majority of consumer low, reasonably priced speakers, paper or plastic diaphragm. What you want out of a speaker diaphragm is something that's stiff, rigid, but lightweight,
Mhm.
because you want the material of the diaphragm to be stiff enough that when you drive it really hard, it doesn't go nonlinear. You want that
Mhm.
whole diaphragm to just stay consistent and not muddy the audio. But what you'll see in paper or plastic, because they're very, very, very pliant materials, when you drive it really hard, part of the diaphragm goes up, part of the diaphragm goes down. This is a concept called speaker breakup, and
Mhm.
that will muddy the audio. And it's most present in the mids and the highs, not
Mhm.
so much in the lows. So we, being a monolithic semiconductor speaker, our speaker diaphragm is silicon. And silicon is 95 times more stiff than paper or plastic. So you have a stiff and rigid material pushing up and down, generating sound. It does not go nonlinear. It does not muddy the sound. So you're getting more pristine mids and highs that you wouldn't get from a conventional speaker.
Interesting. Amazing. Very, very cool. One of the things that the audio engineer that you shared, he was talking about it. He talked about pistonic pressure, which is something that he said you typically get with many different headphones or earbud solutions. What is that? Why don't you have it?
Sure. So a conventional speaker, that paper or plastic diaphragm is typically isolated or sealed front to back. the front of the speaker and the rear of the speaker are not exposed to each other.
Mm.
So in the front chamber of that speaker, the part that's connected to your ear, you have that pistonic motion of that speaker diaphragm, that coil and magnet pushing up and down, and it's pushing air to generate sound, but it's also creating, in a vacuum, it can create some pressure buildup in the ear.
Mhm.
That's why some earbuds typically have a spatial vent in the front chamber to vent out some of that pistonic pressure. But even though they have that vent, it can still lead to fatigue over time. If you're going to watch a movie on a plane for 2 hours or be on your earbuds for multiple hours, it will lead to fatigue. I think everyone's felt it. Um, what's unique about our speakers, again, we're dealing with micron level precision of a semiconductor process. We can actually do what conventional speakers is kind of a no-no. We can actually integrate micron level splits in our speaker diaphragm, because again, we got that micron level precision that as we are doing that pistonic pressure, there are little vents that are opening up and any pressure that's building up leaks out the back.
Mhm.
So what we've observed in our own testing, our testers are working with our speakers every day. We've got them in our ears. We're just sensing that we can keep these earbuds in our ears longer without having those senses of fatigue.
So sounds super cool. What's the path to market dominance, and is it related to the announcement that you're going to make?
Well, we're at the leading edge of that right now. So we've been in the market with product since 2020. We've been in, we've completed our production qualification with our fab and our manufacturing partners since 2021, 2022. So now those production speaker chips are now in the process of being integrated into consumer products, and those consumer products are now reaching production. There are a few products out in the market today using our speakers. More on kind of the niche market side, we've got some kind of hi-fi audio earbuds, probably $1,000 products that
Mhm.
believed enough in the sound quality of our speaker to say that this is different and it's worthy of $1,000 price point. Those are in the market now. So you can buy in-ear monitors for hi-fi audio with our speakers in them. There are some hearing assistance products on the market, hearing aids with our technology. But in November, there will be our first TWS customer, True Wireless Stereo Earbuds, reaching the market with our speakers. So we're at that kind of that cusp of, getting into high volume, mainstream consumer earbuds. That is happening in very short order.
So if somebody wants to check it out, wants to try it, maybe they want to buy $1,000 pair of headphones, or maybe they just want something that's $100, $50, whatever. Are there any brands that are having this in the market right now that they can check out?
Yeah, absolutely. So on the kind of the hi-fi audio side, there are two, you know, premier grade in-ear monitors. One from a US company called Singularity Audio is a very high-end in-ear monitor, about a $1,500 price point. And then there's another Asian in-ear monitor company called Ceranic that also has an in-ear monitor with our MEMS speaker in it. So those are premium products, high price point, really for the audiophile who invests in audio equipment. But really our interest as a semiconductor company is high volume business and reaching that mainstream consumer. And there's a forthcoming product announcement for middle of November from Creative Technology, a well-known brand in both consumer audio and PC and gaming audio. They are releasing a true wireless stereo earbud with our MEMS speakers. They will be the first MEMS speaker TWS brand on the market. And that is coming to market at a very consumer friendly price point.
Very cool. Very cool. Interesting. And do you and have you patented this technology? Is it possible for others to do the same? Or like if this takes off and everybody starts demanding this and Apple wants it in their AirPods and everything else, do they have to get it from you?
Yeah, so we've been very aggressive in patenting all of our innovations. We have well over 110 patents granted. I mean, we're a 5-year old company, and we already have 110 patents granted, covering all aspects of our technology, our process, our manufacturing methods. So we've got good freedom of operations for ourselves and for our customers. With that said, there are different ways to design the product,
Mhm,
and this is a large enough market where we would expect to have competition. So
mhm.
I wouldn't say that we're going to be the only source in the world to get this stuff. That's not going to be true. But we're certainly ahead of the market, and we've got sufficient protection to have freedom of operation.
So you're obviously looking at earbuds and headphones first, but there are speakers all over the world. There's speakers all over the place, and as we add intelligence to just about every product we have, sometimes the ability to speak to it is handy, and certainly with Alexa devices and Hey Siri, at risk of getting Siri all upset here, or other things like that. I mean, there are speakers all over the world. Do you have grand visions of being in everything?
Yes. So the 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 North Star of the company was to not just reinvent personal audio speakers. The North Star of the company is to reinvent loudspeakers. So it's the speaker in your phone, the speaker in your watch, the speaker in your TV, your smart speaker, um, your car, your home entertainment system. We want to touch every corner and nook and cranny of the speaker market. The easier lift for us, the fastest path to market is getting close to the ear. So starting
Mhm,
in personal audio was that easier lift to get to market, get the revenue base going, and to continue to fund R&D for the bigger lift, which is to produce full bandwidth audio in free air, in free space,
mhm,
in
mhm.
a little thin semiconductor chip. So you can imagine the physics challenges that have to be overcome to achieve that. So we're taking things in a logical, staged approach to open up different corners of the market as the technology matures.
As you do that, that looks interesting, and I know that's not your initial focus, but if you look at a Sonos or you look at some of the other big stereo brands, I mean, I'm assuming that you can scale up the physical size of your chip, not the chip per se, but the bit of silicon that's doing the resonating and make it work in a larger environment?
Yeah, so this is where the fundamentals of semiconductors, instead of being a benefit, as we've talked about, actually become more of an inhibitor. If you want to, the logical approach would be, well, if I've got a 6-inch mid range or
Mhm.
a 6-inch woofer, okay, I'll replace that with a 6-inch semiconductor speaker. And pretty soon you've consumed an entire semiconductor wafer to
Wafer,
produce
the
one
whole
speaker.
thing.
And, just financially and fiscally, that just won't make any sense.
Yep.
Semiconductors are good when they're small. So that presents a physics problem, which is how do you produce sophisticated sound in free air in really tiny packages? And again, if you look at the side profile of a conventional, say, tower speaker in a home entertainment system, that speaker has some depth to it. Why
Mhm.
does it have depth? It needs displacement
Mhm. Mhm.
to push air. Okay. So fundamentally, a semiconductor will always be at a disadvantage from a physics perspective. You don't make semiconductors thicker, they're always going to be really thin. So you will never have that displacement of a big, a big free air speaker. So this kind of gets to a forthcoming product announcement that we're going to be making in November, around our Cypress technology, which we are reinventing the transduction mechanism.
I would like to know what the transduction mechanism is.
So the conventional speaker, coil based speakers, even the speakers from XMEMS that exist today, work fundamentally on a push air transduction mechanism. You have an actuator that pushes a diaphragm, moves air, and generates sound. But that displacement is fundamental to your ability to generate sound at distance. More distance, more displacement. We're never going to have that displacement advantage. So we need to find a different way to generate sound. And in 100 years, there hasn't been a product that has generated sound in a different way that could produce equal or better sound. So we are moving to a methodology or a principle of ultrasonic amplitude modulation. So we are using all the advantages of MEMS semiconductors, which is speed, which is uniformity, consistency, to basically build an ultrasonic modulation, demodulation scheme to move outside of the audio frequency spectrum, operate in ultrasonic regions to modulate and demodulate, and then extract. You basically modulate a series of air pulses to the original audio signal. Then you demodulate the ultrasound and extract the audio. So
It sounds very sci-fi.
it sounds sci-fi, and actually sound from ultrasound has been in research mode since the 1960s. And no one has been able to achieve a performance significant enough to commercialize this in a broad way until now.
Mm-hmm. Mm-hmm.
So what this ultrasonic modulation demodulation scheme gives us that our current generation speakers don't, is additional. You've already listened to our first generation speakers. That's full bandwidth audio. You heard, the lowest frequencies to the highest frequencies. But if you want to move into freer air applications or leaky applications, you need to displace more energy in the low frequency. So by moving into ultrasonic modulation and demodulation, we are now putting ultrasonic air pulses into the audio envelope. And low frequency energy is wider. It's wider wavelengths.
Yes.
So we can put more air pulses into a wider wavelength, low frequency energy, so that more air pulses generates more air pressure, which generates deeper bass.
It sounds amazing, but I'm totally missing how the ultrasound, which I cannot hear because it's above the hearing frequency that my ears, especially my ears, I'm not 22 anymore.
Yes.
But above the frequency that my ears can hear, how that gets translated in my open air environment, maybe my home theater, whatever, to something that I can hear.
Sure. So we're getting an input audio signal from the sound source, whether it's your phone, your laptop, or a receiver at home. We get the input audio signal, and really our controller and driver will then basically implement a ultrasonic air pulse scheme to map each ultrasonic air pulse to the frequency of the audio.
Mm-hmm. Mm-hmm.
So we're going to use that ultrasonic modulator to generate air pulses, but then we're going to demodulate that ultrasound to then extract that audio signal. So it's just another way to generate air pressure to create sound, but outside of the audible spectrum.
Are you almost virtualizing the speaker? Is that a way that you could describe this? Is the actual sound production almost happening outside of the speaker assembly, the new speaker assembly?
No. There's definitely a control and a modulation and an amplification in a separate controller chip, but there's still our MEMS semiconductor that is all the MEMS structures are generating the ultrasonic pulses through MEMS, demodulating through valves, and letting the audio flow through. So there is still fundamentally a speaker that has moving parts in it. but it's now a semiconductor and not a mechanical device.
Fascinating. I look forward to seeing it. Thank you so much for this time, Mike.
Thank you, John.